What we did do yesterday was explain what happens with the web browsing by looking at that capture of the packets. We opened this software called Wireshark, which showed us the details of the packet being sent and being sent back. And what happens is that we take data, which is the web. If we look at the response coming from the web server, the data is the web page. That web page is encapsulated inside a HTTP message, put inside a TCP message and so on, and then sent as bits across a link and forwarded across a network. So what we came up with was some packet is sent across the network which contains data. So the data in our example was some HTML, and that packet has a number of headers attached to it which are overhead in our communications. Then we got towards the end of the lecture yesterday, we spoke about performance metrics. How can we measure the performance of a communication system? One of them we saw an example was data rate. I showed you a test with my wireless LAN. I had a data rate of 11 megabits per second, but then I downloaded a file and the throughput was something like 3 megabits per second. I can't remember the value, but much less. So we differentiate between the data rate, the rate at which we can send bits across our link, and throughput, which is the rate at which the real useful data is delivered to the destination. Let's do a simple calculation of what throughput could be achieved, the maximum throughput that could be achieved if we encapsulate some data inside a number of different packets, inside a HTTP packet and so on, by looking at how much overhead the packet headers contribute. If we have our HTML page, on top of that we have a HTTP header, and that has some size. That is a number of bytes in length. Let's give a value to that. As an example, let's say our HTML is 10 kilobytes. The length of the HTML, the data which we want to transfer, is 10 kilobytes. The HTTP header, and I've just made up some numbers here, is 48 bytes. Not kilobytes, bytes in this case. Different exchanges may have different size of headers. So this number 48 I've just made up just for the example. A real exchange, if we looked at the capture from yesterday, we would see an exact value. In fact, it was much larger than this. But just some numbers so we can calculate. And in fact, this 10,000 bytes of data, for reasons of the different protocols being used, is not realistic, but it's just a number that's easy to calculate. Then TCP, so if we remember, the source computer takes the data, puts it inside a HTTP message, so adds the HTTP header, which eventually is sent to the transport layer, put inside a TCP segment, which has some header, let's say is 20 bytes in length. Remember, the header includes the source and destination port numbers to indicate this data is coming from some specific application on the source computer and going to a specific application on the destination computer. The application is identified by the port numbers in the TCP header. The computer on the internet is identified by the IP addresses inside the IP header. Let's give that some size, 20 bytes. These are very close to reality, these two sizes. The size of an IP and TCP header is around 20 bytes. And yesterday we exchanged data over a network. To keep it simple for this example, let's say we're exchanging this packet, this data, over a single link. That link uses Ethernet as the data link layer and physical layer technology. So the source computer creates the data, creates this packet and puts an Ethernet header on there. And in fact, Ethernet adds a trailer, something to the end. Let's say the trailer is 4 bytes and the header is 14 bytes, which is about close to reality for an Ethernet packet. The size of the headers and exactly what's in them is part of the standard that defines the protocol. In the front, in this case, we have something in the front and something at the back. But they have the same purpose, to carry some extra information to support the protocol. And all of this, let's say this Ethernet frame, inside our source computer, it starts with some data at the top. It flows through the stack from the application to the operating system to the LAN card, the Ethernet LAN card. We have this Ethernet frame, and it creates, the LAN card creates or has a sequence of bits representing this. For our example, let's say the Ethernet physical layer adds another 2 bytes of header. The physical layer introduced some extra bits as well. This entire sequence of bits is then transmitted as some signal across our link, some electrical signal across a copper wire or a pair of copper wires. Received, processed, and eventually the data is received by the application. So we have 10,000 bytes of real data plus this extra overhead contributed by the headers. Our data rate of our link, let's set it at 1 megabit per second. All right, Ethernet is in fact more likely 100 megabits per second, but let's just set it at 1 megabit per second. That's the maximum speed which we can send bits across that link. So the signal that comes out, each part of the signal represents a bit. And we can send 1 million bits every second, no more. That's our data rate. What's our throughput, or our maximum throughput in this case? If we had a large file to transfer from A to B, and the way that that large file was transferred by simply sending packets of this size continuously, what would be the throughput? Or if we just focus on this individual packet, what's the throughput for delivering this data to the destination B? We can send 1 million bits per second, but of those 1 million bits we're sending every second, only some of them are actual useful data for the user. And throughput is a measure of what is the rate at which that useful data is successfully received. Let's assume that there's no errors. Whatever we send arrives successfully. In real life there could be errors and it's more complex. Well, how do we calculate throughput? What's the total size of this packet? Or the set of bits that we need to send? It's our 10,000 bytes plus, what's this, 40, 88, 90, 104, 108. The total size of this packet is 10,108 bytes, just the summation of all those components. So in fact, to deliver this data from A to B, we need to send 10,108 bytes. How long does it take to transmit 10,108 bytes? Answer? How are you going to calculate that in your quiz next week? How long does it take to transmit this one packet from A to B? Again?
Not yet. I'm calculating.
How would you calculate? What's the steps? What do you care about? Data rate? Size of packet over data rate. We've got 10,108 bytes. We can send at 1 million bits per second. Therefore, we can get the time to transmit 10,108 bytes. These are in bytes, data rate's in bits. Let's convert. So multiply this one by 8. That's how many bits we have to transmit. The speed at which we can transmit is 1 million bits per second. Data size divided by data rate. Just check the units. Bits divided by bits per second. Bits divided by bits cancels out or becomes 1. 1 divided by 1 over seconds becomes seconds. So our units, the answer of this is going to be seconds. That's what we want. How long does it take to transmit? Measured in seconds. What is it? .864 milliseconds. Simply 80,864 divided by 10 to the power of 6, or 1 million. One of the handouts you have printed lists some very basic mathematics and some units that we commonly use. You should have a look at that before the next quiz. But things like milli, micro, nano even, kilo, mega, giga, these prefixes that we use, make sure you know the difference between them. And we know that 10 to the power of 6, if we divide by 10 to the power of 6, we'll get micro. So this is 80,864 microseconds, or 80.864 milliseconds. So life will be easier when you can quickly convert between milliseconds, microseconds, kilobytes, megabytes, and so on. You can quickly identify the difference. Feel free to use a calculator. In a quiz, in an exam, calculators are allowed, always. In my exam. That's the time to transmit this one packet across our link. Our throughput is the rate at which we successfully receive the real data. So the amount of real data received per second. Well, how much real data do we receive when we receive this packet? $10,000 times. Okay. The amount of real data is 10,000 bytes. We're sending the entire packet. It contains 10,000 bytes of real useful data, times by 8 to get our bits. And the time it takes is what we just calculated. We're omitting any other times like processing time, even propagation time, to keep it simple for now. This is in milliseconds. And the answer, you'll use your calculator for that. Why do I have point in the middle? You mean here, as opposed to down here, or in the middle of what?
I don't know, like, is it like AX0 point, like normal point, or?
It's just like a dot product.
Oh, okay.
Okay.
Yeah.
Is that okay? Yeah, same. Yep. I just try to make it big, no, so it looks like a decimal, not anything else. Okay. So it doesn't look like a comma. So sometimes I'll put it in the middle so it's not down low, it looks like a comma. Yep, it's a decimal place. Use your calculator and you get, I've done it before, 989, that's a 9, 989,315 bits per second. 80,000 divided by 80.864 milli, remember this was in milliseconds, we need to convert it back to seconds, 989,315 bits per second. That's our throughput in this simple scenario. Our data rate of our link, 1 million bits per second. Our throughput slightly less, 989,000 bits per second. Why? Because we're sending our bits over our link. Many of them are data. 10,000 of them are data. But another 108 bytes are overhead, the headers that must be included for the protocols. We can't avoid sending them because they are needed for the protocol to work correctly. But from the user's perspective, they are overhead that we don't really care about. We care about receiving the data. So our throughput of 989 kilobits per second. Also, if you can see this, we could say we have an efficiency of 98.9%. Our link rate is 1 million bits per second, but our throughput is 989,000 bits per second. In terms of the efficiency of using this link to transport real data, we're using 98.9% of it, which is just this number divided by 1 million, but expressed as a percentage. So in this simple case, we could say that, okay, we've paid for a 1 megabit per second link. When we transport data in this scenario, we're using 98.9% of it to transport the real data, the user data, across that link. In this case, I calculated efficiency as simply, yes, the ratio of the throughput divided by the data rate. Unfortunately, that's not a general formula that you can use throughout the course. As we get more detail into how protocols work, it becomes more complex to calculate. Even throughput can become more complex to calculate. In this case, we just sent one packet. In real life, we need to send many packets, and there may be spacing between packets. I send one packet, and then I do nothing for 5 seconds, and then send another packet. So calculating throughput and efficiency can be quite complex in real life. In this case, quite easy. Amount of real data divided by the time it takes to send it. Any questions on how that calculation was performed? Everyone can answer such a question in the quiz next week. You could look at it from a different point of view and think, okay, I've got 10,108 bytes I need to send. 10,000 are real data, 10,000 divided by this number will give you 0.989, so on. The fraction of real data divided by total data. And then that gives us our efficiency. And then if we're using 98.9% of 1 megabit per second, the throughput will be this. Same mathematics, but just look at it from a different perspective. To make sure you understand it, let's give you a test. Let's do it on the screen. So that's, in that example, we really followed this approach where we take our data, add the headers through the protocol stack, and then transmit our signal, our sequence of bits. And we were calculating the throughput. In practice, most technologies, the data rate is known. You buy a technology, you buy your laptop which has a wireless LAN card. That wireless LAN card, part of the specification is the data rate. That's fixed. Or actually, there are different data rates, but they are known. Say 54 megabits per second. It's part of the protocol and standard. The throughput may vary. The throughput depends on many factors. How big the headers are, how often you're transmitting data. Do you have to wait? That is, transmit something and then wait, and then transmit something after some time. The more time waiting, the less time sending real data. What happens if there's an error? You send that packet, the receiver says, no, there was an error in the data, please send again. The throughput only counts the data successfully delivered. So if we have to transmit this one twice, then the total time would be double this, 160 milliseconds, but we only receive one packet of data. So our throughput would halve. So calculating the throughput or knowing the throughput is much more complex. We'd like to know the throughput, but sometimes we do not know in advance. So when you select technologies, you may just know the data rate. Let's give you an example to calculate for yourself. I'll draw the scenario up here. You get your pen and paper ready and you'll calculate it. There's your scenario. A wants to send data to C, but it goes via computer B. Let's say that computer A has a very large file it wants to transfer to C. What it does is it takes that file and breaks it into packets which contain 1,000 bytes of data. And instead of calculating the individual headers, I'll give you that the total overhead is 60 bytes. So the sum of all the headers is 60 bytes in this case. We create a packet, transmit. When it gets to B, B takes the packet and simply transmits it onto C. Assume that there's no or very small processing time in B. That is, as soon as it receives the packet, it can immediately transmit. What's the throughput? Start calculating the throughput in this case. And I'll come around and have a look at your answers.
Overhead is 60 byte or 60 bit.
60 bytes, uppercase B bytes. The first example that I had that we just went through is in your handouts. This one's not. Total size of the headers is 60 bytes. We have two links in this case. You need to understand the significance of those two links. How does that change the scenario? In this case, A is transferring a large file to C. What A does is takes this large file, 1 gigabyte, however size we want to set it, and sends it in chunks, in small pieces. Each chunk, or each segment, contains 1,000 bytes of data. That is, it sends many packets from A to C. So, when A transmits a packet to B, that takes some time. You can calculate that. And then it transmits the second packet to B, and then the third packet, and then the fourth packet, immediately after each other. But note what B is doing. A is transmitting to B the packets. At the same time, the packets that B has received, B is transmitting to C. So you can think this is happening in parallel. A is sending packets to B, and B is sending packets, the ones that it's already received, to C. The question is, we have our applications on A and C. I want to know the throughput from A to C. B is just some intermediate device. I don't care about it. 88 megabits per second? No. 83? 85? No. Throughput? Someone's got an answer?
So I need to transmit time from A to B and then from B to C and then sum it up?
No.
No?
That's the hard part. So the hard part is to know how do the two links work together. Some people are thinking, okay, the transmission time here plus the transmission time here. But what's the throughput for this entire file that we're transferring? Because if you just add up the transmission time, that doesn't make sense, and that's wrong. That if you are transmitting some packets on this link and at the same time transmitting packets on this link, then it doesn't make sense to add up the times, because you're doing it at the same time.
So use the slow one. Okay.
Why use the slow one?
Because the fast one is better than slow one. The limitation is the slow one.
Yeah, the limitation is the slow link here. That is, you think, this we can send at 10 megabits per second. This much faster, 100 megabits per second. We're sending data or packets into B. As soon as B receives them, it can send them to C. And it can send very fast to C at 100 megabits per second. But it cannot send any faster than what it receives. A is sending at 10 megabits per second. B only receives at 10 megabits per second. On average, B will not be able to send faster than 10 megabits per second. Each packet it can send at 100, so what will happen, B receives a packet, sends it at 100 megabits per second, but then waits for the next packet to arrive. And then sends that. So what B is doing is send a packet, wait for 9 units of time. Send a packet, then wait for a long time. Therefore, the rate at which, remember it's a rate, the rate at which C receives a packet, receives nothing. So on average, it's the rate at which, in fact, A is sending. We're limited by this link. What's the throughput across this link? 9.4. That is packet size, transmission time, 0.848 milliseconds. That's milliseconds. That's transmit time for one packet. So if we just focus on this link, the throughput would be simply the data size divided by 0.848 milliseconds. Is something like 9.4 megabits per second with some other values. This is rounded to one decimal place. So the throughput, if we just looked at the first link, is 9.4 megabits per second. But across the path, we're limited by this link. Over time, remember, we need to think that, okay, we're not just sending one packet, we're sending many packets. We've got a large file to transfer, sending one packet at a time. Send one, then another, and at the same time as B receives one, it transmits. So this is sending at 10 million bits per second. Right, we have some overhead as well. This would be on average receiving. So this one's always sending. It's always got data to send. It's always sending at 10 million. This one's receiving at 10 million bits per second on average, minus the overhead. So in fact, it's receiving at 9.4 megabits per second of real data. And therefore, on average, it can only be sending onto C at 9.4 megabits per second, on average over a large period of time, which is, if we draw on over time, what is B doing? For some period of time, it sends a packet from B to C at 100 megabits per second, so it sends it quickly. Transmission time is what? Is 0.08 milliseconds. But then it does nothing. And then it transmits another packet. It does nothing for this period of time because it's still waiting to receive the next packet from A. It cannot send what it doesn't have. So B receives a packet, sends, waits for the next packet to be fully received, which takes 0.848 milliseconds. So this time would be 0.848 milliseconds. That is, B received a packet from A. It can now transmit it, but it will not receive the next packet until another 0.848 milliseconds. And then it transmits it to C, and then another 0.848 milliseconds, and it will transmit the next packet. So the rate at which C is receiving these packets, 1 every 0.848 milliseconds.
So you can say that you just focus on the solid right?
Yes, so
You just don't care about the packets.
yeah, so in general, in a network or a path of links, the minimum of the link data rates is going to limit the path performance. Yeah, this is what, yeah, the bottleneck is the word for this. This link in the path is the bottleneck, it's the minimum. We cannot send faster than that on average across the path. So the good next point is, what if we swap them around? I'll explain that in 1 minute. So make sure everyone's clear on this one. This is what's happening from B to C. Even though it can send quickly, in fact, the transmission time of a single packet is something 0.0848 milliseconds. It's 10 times as fast as this link. The transmit time on this link was 0.848. Transmit time on this link is 1/10 of that. But we spend a lot of time doing nothing. Throughput's about the rate at which the real data, which is this portion, is received at computer C. One packet every 0.848 milliseconds. Each packet contains 1,000 bytes. So the answer is simply 1,000 bytes divided by 0.848, 9.4 megabits per second. So, what happens if we reverse the links? Swap the links. This one is 100, the other one is 10. Same, except more complex. We need some assumptions now. What would happen? Same, because yes, we still have the limit of the 10 megabits per second. But what else is going to happen in this case? What's going to happen at B? B has to carry some. What do you mean by carry? Yeah, B would need to store some of the data that it receives. Look what happens. This is 100. This is 10. We're sending data fast to B at 100 megabits per second. B receives that and then sends it on to C, but at only 10 megabits per second. Where is the rest? So every second we have 100 megabits coming into B, but only 10 coming out. Where is the other 90 megabits every second?
Some buffer.
Stored in some buffer, some piece of memory inside B. The packets come in, are stored in memory. When the packets have been sent out, then they'll eventually get to the head of the queue in that memory, in the buffer, and then are transmitted. So importantly, what happens is that packets will be queued up. They'll have to wait in some queue inside B. And we'll see on the slides later, that will introduce some queuing delay. How big, let's say our buffer is 10 megabytes. What's going to happen? If I keep transferring a very large file, what's going to happen at B? The buffer will fill up. We're adding stuff to the buffer, sending out slowly. Eventually it will fill up. The memory fills up, something goes wrong. The computer crashes. This one, depending on the protocol, should somehow inform A, slow down. Don't send so fast. You're sending too fast for me. Because I can only really send at 10 megabits per second. Slow down. That mechanism we're going to cover after the midterm, how that works. But the point here is that as packets come into B, they'll be queued, put in some queue inside memory, in a buffer, and packets will have to wait before they're transmitted. That incurs some queuing delay. So now we know something about throughput, let's look at the other performance metric of delay and summarize what that is. So before I hide this, any more questions?
About efficiency, which one we have to consider? 10 megabits per second or?
Efficiency is not. So now, what about efficiency? How do we calculate efficiency? Well, it's not so easy to calculate in a network, in a path, because what do we cannot say it's divided by 100 or divided by 10. So in fact, I don't think we can easily talk about efficiency in this case.
Consider 10, we have 94%, but only 9%.
So we could say we are 94% efficient in using this link, 9% efficient using this link. We're sending at 9 megabits per second on average, and at 9 megabits per second. A lot of the time on this link, we're not using it. That's inefficient. So we can only look at individual links in that case. Of the second case, the red case, how do we calculate the throughput in this case? Assume we have an infinite buffer. If we ignore the fact that the buffer would overflow and start to lose, I think we could show that it's the same. It's the 9.4 megabits per second.
It's like moving data from A to B and then B to
Yes. In real life, or a good protocol would control the speed at which A sends. Limit the speed at which A can send so that it's no faster than 10. But that's more complex. In this case, we would keep it simple and say, okay, the limit is 10, the throughput is still 9.4 over the network. But that ignores many things that happen here.
So if we switch the same throughput, if we have to assume that we have buffer.
Yeah. Yeah.
The answer is
And then it works perfectly, the
we
buffer.
have to assume first, and then the throughput
Yeah.
is the same as the first case.
Yeah. I don't think I'd give you a question at this stage in this reverse situation unless it was about what happens at B. The main point here is what happens at B. Buffering occurs. Queuing delays incur. How much? We don't care so much. Let's return to our slides and then come back to an example. If this will stay down. That leads us to delay. Delay is different. It's another performance measure. When I'm talking on the phone, over the internet, using voice over IP, then we care about when I talk and when the other person hears my voice, there's a very small delay. We don't need a high throughput for voice. We'll find out with voice calls you can survive with tens of kilobits per second to get reasonable quality voice. But you need a very short, controllable delay. Delay, we can say, is made up of 4 components. If we draw our simple network again of 3 devices transmitting data from A to C via some intermediate device B, what are the components of delay that may be incurred? Well, first, each of these are computers. What we do is we take the data, the application looks at it, does some processing, sends it to the operating system does some processing, sends it to the LAN card, the hardware, and then that eventually transmits some signal onto the link. There's some potential processing delay. That is, it's a computer, it has some data, it needs to do some processing, that takes time. How long does it take? It depends on the computer to the main extent and partly on what the protocols need to do. It's very hard to calculate in advance what the processing time of one packet is going to be. One computer could be completely different from another computer. Different devices, a mobile phone compared to a router, a commercial router, maybe orders of 10 or 20 times different in terms of the processing time. So processing time happens at each device. There's a processing time at A, at B. B receives some data, processes it, looks at it. When I say process, the computer does some operations on it. And C, when it receives it, does some processing. Usually, compared to the other components that we'll see, this is quite small. How long does it take my laptop to process a packet? Maybe in the order of nanoseconds and microseconds. We'll see that the other components of delay can be much larger. So sometimes we'll ignore processing delay. Because we cannot calculate it, it's either going to be given, okay, the processing delay is 1 millisecond, or ignore it. Say it's so small that it's not going to add much to the total delay. But there is some processing delay. Computer A takes the data, processes it, transmits onto the link. There's some transmission time. Transmission delay. This depends upon the amount of data that we need to transmit and the speed at which we can transmit. And we can calculate that. We've calculated it in the previous examples. The size of the data in bits divided by the data rate in bits per second gives us the transmission delay. Think of this as how long does it take for your computer to get that packet, that piece of data, out onto the link. The link allows us to transmit at 1 million bits per second. If we have a link data rate of 1 megabit per second, write that clearer. Megabits per second, sometimes I write P for per second or a slash. Then 1 bit can be transmitted in 1 microsecond. 1 million bits in 1 second, therefore 1 bit can be transmitted every 1 microsecond. So therefore there's some delay to transmit all the bits. Simply the data rate, data size divided by the data rate. That's for each link. There's a transmission delay for A to transmit the bits onto the link. When B receives the data, it needs to transmit them on this link. There's a transmission delay also here. How are we going to do this? It's also a transmission delay if we say, think of it transmitting onto the link, from the source node to transmit onto the link. Inside each computer device there's a processing delay. To use each link there's a transmission delay. What we do, we take the first bit of the data, transmit it as a signal onto the link, take the second bit of data, transmit it as a signal, and so on. Each bit that we transmit as signal propagates across the link. If we transmit it as some electrical signal, say some sine wave, we start transmitting, depending on the distance of the link, that wave needs to propagate across that link. That's the propagation delay. So we have our propagation delay, and that depends upon how long the link is, the distance in meters, and the speed at which our signal traverses that link. The units here are bits and bits per second. The units here are meters and meters per second. So this is depending upon the physical signal that needs to be transmitted. If the best that we can transmit a signal is the speed of light. The speed, if we're sending in a vacuum in a perfect conditions, then we can send a signal at the speed of light, no faster. All right, if we're sending across a cable, if we're using optical fibre, then in fact we get close to the speed of light. Maybe not 3 by 10 to the 8 meters per second, maybe 2 point something by 10 to the 8 meters per second. Sending electricity across a copper wire, again it's close to, maybe 1 or around 2 by 10 to the 8 meters per second. The speed has a maximum of the speed of light, which is around 3 by 10 to the power of 8 meters per second. Different media may have different speeds in practice. We don't know, that would need to be given to you. It's a characteristic of the media.
So we have to consider it a lot or not?
Yes, we do. We'll see why in some cases. So we take the distance of the link divided by the speed. When is it significant? Well, it depends upon the distance, and it depends upon also the transmission delay. We'll see later the relationship between these two are quite important. 10 meters, very small propagation delay. 10 divided by 300 million seconds, which is 0.03 microseconds, matter of nanoseconds. What about you sending to a satellite, which is 36,000 kilometres away? Then the propagation delay can be quite significant. We'll calculate that shortly. The signal needs to propagate across this link. When it's received, B sends across the next link, also with a propagation delay. So we can say each computer has some processing delay. Each link, we have a transmission delay plus propagation delay. Finally, in some cases, we'll have queuing delay. We saw that example just previously, that packets could arrive at B. Before they can even be processed and sent, they need to wait for the other packets to be sent. They need to wait in a queue. There's no easy way to calculate what that will be. In large networks like the internet, that's quite variable. It changes over time. It can be very small, it can be quite large in some instances. We can calculate for a link transmission and propagation delay. Processing delay is usually quite small. Queuing delay can be quite significant in a large network, but not easy to calculate. In fact, there are entire courses to calculate queuing delay. Total delay is the sum of all the components. To get our packet from A to C, it's the processing delay here, plus the transmission, plus propagation, plus processing, plus queuing, plus transmission, plus propagation, plus processing. There may be queuing here, and that's the total delay to get that packet from A to C, the summation of all the components. Example for you to calculate again. Here's our satellite scenario. In satellite communications, up in space there's a satellite, and in this case what it does, on the ground, here in Thailand we have a ground station which transmits a signal up to the satellite, the uplink, and the satellite takes that signal or the data and simply retransmits it down to a receiving ground station, the downlink. Somewhere else. So we can communicate between 2 points on the ground via that satellite. Let's assume we have our source computer here and our destination here. You will calculate the total delay to get a packet, just one packet from source to destination. Assume the following. Uplink has a data rate. Let's get a different one. 1 megabit per second. Downlink just to make it different, 100 kilobits per second. Our packet size just make it 1,000 bytes. Ignore overhead here. We just look at the delay for the entire packet. That may include headers and data. We care about how long does it take to get that one packet, that one message. And how far is the satellite from the Earth? Well, a typical geostationary satellite, one that is in an orbit such that as the Earth rotates, the satellite rotates with us so that it looks like the satellite is always above us. It's called a geostationary orbit. 36,000 kilometres. That's the distance from the ground station to the satellite, and similar from the satellite down to the ground station, the second ground station. Speed of light, you can assume 3 by 10 to the 8 meters per second. What's the delay? Let's say the satellite has a processing delay of 4 milliseconds. Processing delay in the ground stations is very small, 0. Queuing delay, there's no queuing at the satellite. It receives, sends, with some processing delay. Calculate the total delay.